Thank you for the introduction. I will present a work in my paper here. Hello, everyone. I'm Zheng from Fudan University, and today I'm very glad to present our invited paper, a joint effort with UC San Diego on building a more reproducible benchmarking foundation for 3D physical design research. Here is the outline today. I will first introduce the reproducibility problem, then the PIN 3D enablement and the flow, followed by several validation results, and finally the main takeaway today. So let's start with the background of today's physical design research. This slide shows the main gap we want to address in both 2D and especially 3D physical design research. Fair comparison requires a complete evaluation flow together with consistent metric and logging. However, reproducibility is still a major gap today. First, there are too few shareable test cases because industrial designs are usually restricted by IP and NDA limits, while public benchmarks are limited in both scale and diversity. Second, benchmark formats and tool interfaces are fragmented, so it is difficult to move a design across tools and rerun a complete flow consistently. Third, flows are often incomplete or unstable over time, and metric definitions can vary across setups, which makes published results hard to replay and compare fairly. So we propose Rosetta Stone 2.0. This slide introduces Rosetta Stone 2.0. Which we propose as a benchmarking backplane for academic physical design research. Rosetta Stone 2.0 improves transparency through three parts: benchmark translation, benchmark expansion, and flow execution. For benchmark translation, we convert academic benchmarks and real PDK assets into a unified representation in OpenDB. For benchmark expansion, a recent work at Net can generate scalable synthetic netlists that remain realistic while helping protect IP. This is especially useful when real shareable test cases are limited. For flow execution, we provide a plugin-based runtime together with standardized logging and metrics. This allows us to integrate tools in open road research together with TCO-based flows in ORFS research under a more consistent evaluation framework. So with this backplane in place, I will now move to the 3D part of the talk, PIN 3D enablement and flow. This serves as a concrete example of how the Rosetta Stone 2.0 plugin flow concept can be used in practice. This slide introduced the key idea behind our unified 2D abstraction for face-to-face 3D stacks. We built a 2D abstraction for face-to-face stacks so that standard 2D tools can operate on the design. The key idea is to duplicate and align the two-tier routing stacks into one unified physical view. For cross-tier connectivity, we introduce an HB cut layer between the two tiers. The hybrid bonding terminals, or HBTs, are modeled as vertical connections between the two dies, so cross-tier connectivity can be represented explicitly. From the tool's point of view, the design now looks like a unified routing environment with controlled routing layer access. This allows us to reuse mature 2D engines to run the flow on a 3D stack. Some extra routing layer handling is needed to match the open rows pin access assumptions. But the key point here is that the flow still runs with standard 2D engines. Overall, this abstraction makes a 3D design appear as one unified 13-layer environment to unmodified 2D engines. And this slide shows how we support tier-by-tier optimization. We build tier-specific PDN grids, and this separation is especially important for heterogeneous integration. And to support die-by-die optimization, we generate tier-specific physical views. For each left view, we generate upper dot left and the bottom dot left with the correct layer mapping and the core views. However, overlaps may still be detected between core cells, even when they are placed on different layers. To address this, we also generate upper dot cover dot left and bottom dot cover dot left. With these cover views, one tier can be optimized while the other remains transparent and fixed because overlaps between cover cells and core cells are ignored. To prevent unexpected cell insertion on the hidden tier, we apply tier-specific do not use controls. There are some differences for heterogeneous PDK I want to point out. So for the heterogeneous integration, we introduce a tier map for cross-die cell movement. When a cell moves across dies, we need a one-to-one mapping between the two libraries that preserves, for example, site legality and logical equivalence. This mapping defines the correspondence between cells across the two tiers. Even with a good cell map, heterogeneous tiers may still have different cell heights, site definitions, and row constraints. So we need to reconstruct the rows for each tier to keep placement legal and snapping consistent. So far, I have shown how we build 3D PDK from 2D technology data and how we support tier-by-tier optimization. With the framework, we release 3 PDKs, non-gate 45 3D, ASP7 3D, and heterogeneous ASU7 plus non-gate 45. On top of that, we provide a fully automated RTL to GDS flow for face-to-face 3D stacks by reusing mature 2D engines. The flow starts with 2D logical synthesis using the 2D PDK, followed by partitioning with Triton part. At this point, we generate the 3D depth, left, and Verilog representations for the next stages. Next comes 3D floor planning. We create the die and the core areas, assign pins to specific layers, perform macro placement die by die, and then build separate 3D PDNs. Then we optimize one tier while keeping the other fixed and switch between them. This lets us reuse mature 2D tools while still achieving 3D co-optimization. Then we perform CTS on only one active tier, either upper or bottom, using a 2D tool. As a result, clock buffers are inserted only on the active tier. Finally, routing is performed under the unified multi-layer abstraction, while HBTs are treated as special vertical connections, so the complete flow remains automated from RTL all the way to final implementation. To make the flow reproducible, each stage has explicit handoff artifacts. These artifacts are kept in standard 2D friendly formats and can be stored and exchanged through OpenDB, which supports replayability and clean tool swapping. In the third section, I will briefly highlight several validation results. I will keep this part short because our main focus today is the methodology rather than chasing a single PPA numbers. Our mixed two-chain study shows that Yosys causes the largest degradation in area and power. And it also shows that the main open source backend gap is in CTS and routing, especially in physical convergence and design rule closure. We also study HBT pinch sensitivity. Larger pinch makes HBTs behave like larger routing obstacles and causes more routing violations, while via scale pinch greatly improves routability and design rule closure. Finally, let me conclude with the main takeaway of this work. To conclude, this work is not only about QOR, but about building a more reproducible, comparable, and extensible infrastructure for 3D physical design research. Our goal is to narrow the gap in 3D PD research and make it easier for researchers to build and evaluate new ideas. So our code and reference flows are available on GitHub, and the ORFS research Pin 3D materials can be accessed through the QR code on this page. I'd also like to thank our collaborators and supporting institutions for this joint effort. Thank you very much for your attention. I'm happy to take questions now.
Any questions?
Yeah? Do you think we could add a blockchain system over this whole set of things and make it anonymous so that we could get hash and reviewers could get a hash so that we could verify stuff that has to run through these systems? That would be a really big improvement.
I'm not sure because I think the open source. I think the open source tools you can find a specific hash for the specific version of the code, so we can reproduce it with the hash async. I'm not sure if this can answer your question.
No, so I was just saying we propose as a community a mechanism to make it anonymous. I mean, lose area does double blind studies. We are far from that. So it's not necessarily a question to you.
Oh, okay. Yeah, I mean, it's interesting. Like if you wanted to get commercial tools. So actually, I have a question for you. If I'm developing something, let's say CTS or Placer, can I plug in my method into yours, upload it, and put it through ORFS and get all the metrics 2.1 to be processed? How does that work in the framework?
Okay, so I will show you maybe this slide.
Does it plug and play?
Yeah. Okay. We have a handoff outline here. We have a specific output and input in every stage, so you can replace your tool in any of this stage and rerun this flow. So this is our handoff outline.
Yeah, I mean, because there's a lot of works these days using Open Road, so I think maybe this is a good framework if you want to get to repeatability, right? To use your framework and verify it. Yeah, especially with agents, we can do it on the fly. When I submit a paper, I can plug in. I think it'd be very interesting.
One comment is that Professor Zheng, who is GU's advisor, is the maintainer or leader of both ORFS research and open road dash research in the IEEE CETA DATC's GitHub. So, please go there for the latest updates, sort of mission, philosophy, what's ongoing, what's the roadmap, for that kind of information. But what GU describes is one first exemplar of sort of it's working, proof of life kind of thing.
Also talk more about ArtsNet. How are you augmenting the benchmarks?
Okay. So the benchmark, the ArtNet is a work from UCSD, and I'm sure this framework. So the ArtNet can extract parameters from a stored netlist in OpenDB, and it generates an exchange file called a spec file. And this file defines some characteristics for a netlist, and then it can use the characteristics in the netlist to use its generation to generate a new netlist that can be reused in OpenDB, and it will be physical equivalence with the original netlist. I believe this is what the ArtNet do. So this is for the benchmark expansion.
Is it parameterizable? Like if I want to have more Rents exponents in some parts of the circuit, can I add more complexity to the output of ArtsNet to make some designs hard to route or hard to time close?
Maybe, for example, there may be a average fan out of the netlist, or the standard cell ratio in the netlist, or the logic cell ratio in the netlist, and the macro, and so on. ArtNet use this information to generate the spec file, and then we can use the spec file to generate a new netlist.
Oh, so there's a spec, you input the spec and then...
Yeah. Also, timing path lengths are somewhat controllable in the generated netlists.
Any other questions for G and Professor Han? Thank you, G, so much for this great contribution.